Hey guys, welcome to today's video, and today we will be tackling one of the two major problems of calculus. The first major problem of calculus was to find the slope of a line tangent to a curve. That problem is called the derivative, and today we will try to find a definition of the derivative, and we will try to establish some rules of that derivative. First of all, we have f of x, okay? So if we have f of x and we have a point A, then at that point, we want to find out what is the slope of a line that touches only at that one point. Meaning a line that looks like this. What is the slope of that line? How do we find that out? Well, it's really hard to think of a slope at exactly one point, because if you think about it, how do you think of a slope at exactly one point? You need 2 points to have a slope, right? So let's think about 2 points. So let's say we have this point and we have this point, okay? Now let's connect them together and let's have a line. What is the slope of that line? The slope of that line, as we know, slope is equal to rise over run, right? The rise at that point, the rise at this point is equal to, let's say this is just some regular old, let's say some x value, just any x value for all we care. So we could say this has to be f of a, this has to be f of x. Okay? So, you know what? Just for, let's say x naught, just to be safe. Okay? Now, you know what? Let's just keep it normal. What am I doing? Okay, f of x. Okay? Now, slope is rise over run. What is the rise? Rise is f of a minus f of x. And the run is a minus x, right? So we have this to be the slope of this line. So the slope of this line approaches the slope of that tangent line as x approaches a. Think about it like this. If we make x closer to a, then our tangent line becomes closer and closer and closer to the real. Then our slope line becomes closer and closer and closer to that tangent line. For example, if we then choose to go all the way, not all the way, but if we get even closer, then we'll have a tangent line that gets even closer and closer and closer and closer to this line. So since we have something approaching something, it's best that we use a derivative. And we use a limit, sorry. We use a limit to define this derivative. So we will say the derivative, okay, of f of x at a is the limit as x approaches a, because as x approaches a, of f of a minus f of x over a minus x. Or you can write this in a more conventional form, which would be f of x minus f of a over x minus a. Now note, these limits tend to be a little bit hard to solve because as x approaches a, note you'll have a 0 over 0 limit, meaning your limit won't be defined. You'll have to do some cancellation behind the scene. Now this is the derivative of f of x at some certain point. But what about at any point, okay? So let's say we have just any regular old, we just call this some regular old x, okay? Use the blue marker, and we have, okay, we have this graph. Now we have this to be f of x. So now we just have x, and let's say we have some x plus delta x. Okay, so now delta x is the difference between these 2 points. So we have this is not f of a anymore, but that is f of x plus delta x, and now we have this point to be equal to f of x. So this is now that new line. Okay? So that's the new line. And if we want to find the derivative, so if we want to find the slope of that line is equal to f of x plus delta x minus f of x over x plus delta x minus x, or just delta x. And if we want to find the derivative, or the instantaneous slope of x, we need to get x plus delta x as close as possible to x. In other words, delta x has to approach 0, right? So now we have the limit as delta x approaches 0 of f of x plus delta x minus f of x over delta x is equal to the derivative of f of x. So that is the limit definition of a derivative. It's the formal definition of a derivative. This definition is applicable at any point of that derivative, while this is only applicable at some one point. Now, the more conventional notation is not to use delta x, but to use h. In other words, x plus h as it approaches x. However, I believe delta x is more easier to understand. However, for a convention, we will replace that with h. Okay, now let's talk about notation. How do we write the derivative of f of x? One thing that's really common is to write the derivative with a prime. So you have f prime of x is equal to the derivative of f of x. This also means that you can write f prime of a as the derivative of f of x at a. Another thing you can do, this is called Newtonian notation. Newtonian notation. Okay? Another thing you can do is write dy by dx. The thing with dy by dx is that it's as if you had an infinitely small amount of y divided by an infinitely small amount of x. In other words, the instantaneous slope, because it's an infinitely small version of rise over run. So dy by dx, this is Leibniz notation. And as we learn things like integration, we'll learn the usefulness of Leibniz notation. And the thing with writing dy by dx at some point is that it can be a little weird. You have to write dy by dx, then you gotta write a little thing like this, and then write x equals a, which is weird, but generally dy by dx isn't used like this. It's generally used for like more symbols. So we can write, now finally, we can write, that's h. We can write this as equal to f prime of x equals dy dx. Generally don't say dy by dx. A lot of times we just say dy dx. So now that is the limit of a derivative, and now we'll cover something called the power rule, which is used to take derivatives of very common functions. So now we'll be looking at something called the power rule. So we have the definition of the derivative here, which we just derived. The limit as h approaches 0 of f of x plus h minus f of x over h equals f prime of x. So now let's find out what is the derivative of a function that looks like this. Let's say x cubed. Okay, let's find the derivative of the family of functions that look like that. And to be generalized, let's say x to the n. Okay, what is the derivative of x to the n? So let us put it into the definition of a derivative. So the derivative of x to the n is the limit as h approaches 0 of x plus h to the n minus x to the n all over h. Okay, so now let's break this down. Let's use the binomial theorem to break this down. Okay, so what do we have? First, on top, we have okay, we have x to the n plus. Now, if we remember from the binomial theorem, what we have to do now is we take n choose 1, okay, and we get plus n times x to the n minus 1 times h. Now, everything else in here is useless, and I'll explain why. So I'll just write a plus dot 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 minus x to the h. Okay, sorry, x to the n. Sorry, not h. Minus x to the n all over h. Okay, so now we can cancel out this term and this term, and then divide out the h from every other term, and then we get the limit as h goes to 0 of n times x to the n minus 1 plus a bunch of random terms. The reason all those terms are useless is because since they were all after this one, they all had h squared or h cubed or h to the 4th, so they will still have an h now. So as h goes to 0, those are all 0, so we don't need to worry about adding them. So the final result is n times x to the n minus 1. And this is the power rule. So let's write it out. d by dx of x to the n equal to n times x to the n minus 1. Okay? So that's the power rule. So now, if you're taking the derivative of something like x cubed, you just take the 3 to the front and reduce the power by 1, and you get 3x squared. If you're taking the derivative of x to the 8th, you get 8x to the 7th. That's it. So, thank you for watching. Make sure to like and subscribe, and I'll be releasing a video shortly about the product rule and the quotient rule, and also explaining whether you can add with the limit rule, whether you can add with derivatives, and how derivatives add, how derivatives multiply with constant and with other functions. So thank you for watching this video. See you later.